Hello everyone and welcome to our channel Mootechie. It's a pleasure to have you with us as we explore the fascinating and essential topic of colloids. This is a subject that touches everything from the food we eat to the very cells in our bodies, so let's dive right in. Our story begins with Thomas Graham, widely recognized as the father of colloidal chemistry. The term colloid itself has a sticky origin, coming from the Greek word kolla, which means glue. Graham initially categorized substances into two groups, crystalloids and colloids. However, this rigid classification was later reconsidered as science advanced, revealing that many particles could exist in this unique state. So what is a colloid? Fundamentally, a colloidal state is a dispersed system. This means it consists of one phase, typically a liquid, with tiny insoluble particles evenly distributed throughout it. To picture this, think of a dense fog. What you're seeing is a colloid, with countless minute water droplets dispersed in the air. Or consider a wobbly dessert like jelly. That's also a classic example of a colloid. Now let's understand its structure. Every colloid is a two-phase system. These are known as the dispersed phase and the dispersion medium. The dispersed phase is the material that is broken down and scattered. It's also called the internal or discontinuous phase. Imagine dust particles floating in the air. They are the dispersed phase. Conversely, the dispersion medium is the substance that contains the dispersed particles. It's the continuous or external phase. In milk, for instance, water acts as the dispersion medium. To put it another way, a colloid is a substance microscopically dispersed throughout another substance. Remember its glue-like roots. These particles are small enough to pass through a filter paper but are trapped by a semi-permeable membrane. And if you need to separate them, you can use a centrifuge. Colloids are not just laboratory curiosities, they are integral to our daily lives. You'll find them in forms like whipped cream, in milk, in fog and smoke, in detergents, in advanced materials like aerogel, in vital fluids like blood, in the paints on our walls, and in the cosmetics we use. Delving deeper, the colloidal system always has two parts, a dispersed phase which is discontinuous, and a dispersion medium ventium which is continuous. The particles in the dispersed phase are incredibly small, with diameters ranging from about 1 nanometer to 100 nanometers. They are so tiny that they remain invisible under a standard optical microscope. To actually see them, you would need an ultramicroscope or an electron microscope. To fully grasp colloids, it helps to compare them with other mixtures. We generally have three categories: true solutions, suspensions, and colloidal solutions. First, suspensions. These are heterogeneous mixtures with relatively large particles. Think of whole blood or a bottle of medicine that instructs you to shake well before use. Let's break down all three types. True solutions are composed of particles, atoms, ions or molecules that are extremely small and dissolved in a solvent. Colloidal mixtures have particles that are intermediate in size, not as minute as those in a solution, but not as large as those in a suspension. Suspensions contain the largest particles. These can be mixed evenly by shaking, but they will eventually settle out. So to recap, we have true solutions, colloidal solutions, and suspensions. Let's solidify this with concrete examples. A solution. When table salt dissolves in water, it forms a saline solution. The salt is the solute, the water is the solvent. A suspension. If you mix flour into water, it creates a suspension. It might even look slightly blue because the flour particles scatter blue light more effectively than red light. A colloid. Milk is an excellent example. It's an emulsified colloid, where globules of liquid butterfat are dispersed within a water-based liquid. This mixture is stabilized by electrostatics. The mutual repulsion of similarly charged particles prevents them from clumping together. Now let's systematically compare their properties. Looking at particle size, true solutions have particles smaller than 1 nanometer. Colloids range from 1 to 100 nanometers. Suspensions have particles larger than 100 nanometers. Appearance. True solutions are clear. Colloids and suspensions are cloudy. Homogeneity. True solutions are homogeneous. Colloids can be either homogeneous or heterogeneous. Suspensions are heterogeneous. Transparency. True solutions are transparent, though they can be colored. Colloids are often translucent or opaque, but can sometimes be transparent. Suspensions are often opaque, but can be translucent. Separation. True solutions do not separate. Colloids can be separated. Suspensions will separate or settle on their own. Filtrability. True solutions pass through filter paper. Colloids also pass through filter paper. Suspensions do not. Their particles are caught by the filter. Here is another perspective on the comparison. Particle size, for suspensions, it's greater than 100 nanometers. For colloids, it's 1 to 100 nanometers. For solutions, it's less than 1 nanometer. Visibility. The particles in a suspension can be seen with a low-power microscope. Particles in colloids and solutions cannot. Nature. Suspensions are heterogeneous. Colloids are either homogeneous or heterogeneous. Solutions are homogeneous. Setting of particles. Suspensions settle naturally. Colloids settle during centrifugation. Solutions do not settle. Appearance. Suspensions are opaque. Colloids range from translucent to opaque. Solutions are transparent. Filtration. It is possible to filter suspensions but not colloids or solutions. Brownian movement suspensions may show it. Colloids clearly show it. Solutions do not show it. What are some other examples of colloids? The list is extensive. Milk, synthetic polymers, fog, blood, jam, shoe polish, smoke, and more. For instance, cherry blossom shoe polish is a colloid. For a suspension, consider chocolate milk. The chocolate particles will settle if the glass is left undisturbed. And for a colloid, remember blood, a vital biological fluid. For a true solution, think of freshly squeezed lime juice mixed with water and sugar. Now, how do we classify colloids? There are several methods, based on the physical state of the dispersed phase and dispersion medium, based on the nature of the interaction between them, based on molecular size in the dispersed phase, based on the appearance of the colloid, and based on the electric charge on the dispersed phase. Let's start with the first method, classification by physical state. This gives us various types with specific names. Solid in solid is a solid sol. Examples are alloys and cranberry glass. Solid in liquid is a sol. Examples include ink and blood. Solid in gas is an aerosol. Think of smoke or ice clouds. Liquid in solid is a gel, like jelly or curd. Liquid in liquid is an emulsion. Milk and cream are prime examples. Liquid in gas is a liquid aerosol, such as clouds or fog. Gas in solid is a solid foam. Examples are aerogel and pumice stone. Gas in liquid is a foam, like shaving cream. For gas in gas, no colloid forms because all gases mix uniformly to form true solutions. Next, classification based on the interaction between the phases. First, lyophilic colloids. Here, the dispersed phase has a strong affinity for the dispersion medium. They are also called intrinsic colloids. These substances readily form colloidal solutions. When the medium is water, they are termed hydrophilic or emulsoids. They are typically self-stabilizing, reversible, and heavily hydrated. Starch, gelatin, rubber, and proteins are common examples. In contrast, we have lyophobic colloids. Here, the dispersed phase has little to no affinity for the dispersion medium. They are known as extrinsic colloids. They do not form colloids easily and are relatively unstable. They are irreversible and require a small amount of electrolyte for stabilization. They are poorly hydrated. In water, they are called hydrophobic or suspenoids. Examples include sols of metals like gold and silver, and sols of metal hydroxides and sulfides. Visually, you might picture a lyophobic particle being surrounded and stabilized by lyophilic particles. How are these lyophobic sols prepared? One common approach is through condensation methods, where small particles are encouraged to form larger aggregates. Oxidation method. Sulfur colloids are made by oxidizing hydrogen sulfide with O2. Reduction. Silver colloids are prepared by passing H2 gas through a solution of silver oxide. Hydrolysis. Adding iron 3 chloride to boiling water produces a dark brown iron 3 hydroxide colloidal solution. Double decomposition. Passing hydrogen sulfide gas through a solution of As2O3 creates an arsenious sulfide sol. Exchange of solvent. A colloidal solution of phosphorus can be made by adding its alcoholic solution to excess water. Classification can also be based on molecular size. Multi, MOLE, CULAR colloids. The dispersed particles are aggregates of many atoms or small molecules, with diameters under 10 to the power of -7 cm, held together by van der Waals forces. Gold sol and sulfur sol are examples. Macromolecular colloids. Here, the dispersed particles are themselves very large single molecules, big enough to be of colloidal dimensions. These are essentially natural polymers. There's also a special category, associated colloids. These substances act as normal electrolytes at low concentrations, but form colloids at higher concentrations. These are also called Micelles. Sodium stearate is a classic example. It behaves as an electrolyte when dilute, but forms a colloid when concentrated. Soaps, higher alkyl sulfonates, and polyethylene oxide are other examples. This leads us perfectly to a practical question. How does soap work? When soapy water encounters greasy dirt, the soap molecules assemble into tiny clusters called micelles. The water-loving or hydrophilic heads of the molecules face outward, interacting with the water. The oil-loving or hydrophobic tails point inward, trapping the oil in the center, effectively removing it from the surface. Colloids can also be classified by their appearance. When a colloid is fluid, it's called a sol, often named after its medium: hydrosol in water, alkosol in alcohol, benzosol in benzene. When a colloid is solid, it's a gel. Its rigidity varies. Think of jelly, butter, cheese, and curd. Another simple classification is by the electrical charge on the dispersed phase. Positive colloids. The dispersed phase carries a positive charge. Examples are metal hydroxides like iron 3 hydroxide and aluminum hydroxide, and methylene blue sol. Negative colloids. The dispersed phase carries a negative charge. Examples are silver sol and copper sol. How are colloids made or separated? Key methods include mechanical dispersion, electrical dispersion, Bradig's arc method, peptization, and condensation methods. Let's look at mechanical dispersion. The substance is first ground into coarse particles. It's mixed with the dispersion medium to create a suspension. This suspension is then fed into a colloidal mill. This mill has two metallic discs rotating in opposite directions at very high speeds, around 7,000 revolutions per minute. The narrow gap between the discs subjects the suspension to immense shearing forces, breaking it down to colloidal size. This is how colloidal solutions of black ink, paints, and varnishes are produced. Next, electrical dispersion or Bradig's arc method. This is used for metals like platinum, silver, copper, or gold. The metal serves as two electrodes, immersed in a dispersion medium like water, which is kept cool with ice. An electric arc is struck between the electrodes. The intense heat vaporizes some metal, which then condenses into colloidal-sized particles in the cool liquid, forming a sol. Then there's peptization. This is the process of converting a fresh precipitate into a colloid by adding an electrolyte, known as a peptizing agent. The ions from the electrolyte are adsorbed onto the precipitate particles, causing them to break apart into smaller colloidal particles. For example, iron 3 hydroxide precipitate can be peptized by iron 3 chloride. Common peptizing agents include sugar, gum, gelatin, and electrolytes. Finally, the condensation method, where small particles aggregate to form colloidal-sized particles. One way is by passing vapors, e.g. of mercury or sulfur, through a cold liquid containing a stabilizer. Another is by excessive cooling. A colloidal solution of ice in a solvent like ether can be made by freezing a solution of water in that solvent. Or by exchange of solvent. If a substance dissolves in alcohol but not water, like sulfur, pouring its alcoholic solution into water will create a colloidal sol. Chemical methods are also part of condensation. 1. Oxidation. Adding oxygen or removing hydrogen. Colloidal sulfur can be made by oxidizing hydrogen sulfide with bromine water, hydrogen sulfide plus bridge 2, right arrow 2, HBr plus S. Another reaction is 2 hydrogen sulfide plus sulfur dioxide, right arrow 2 hydrogen oxide plus 3S. 2. Reduction. Adding hydrogen or removing oxygen. A gold sol can be prepared by reducing gold chloride with stannous chloride, 2 gold 3 chloride plus 3 tin 2 chloride, right arrow 3 tin 4 chloride plus 2 Au. 3. Hydrolysis. Decomposition by water. A ferric hydroxide sol is made by hydrolyzing ferric chloride in hot water. Iron 3 chloride plus 3 hydrogen oxide, right arrow iron 3 hydroxide plus 3 HCl. 4. Double decomposition used for insoluble salts. An arsenious sulfide sol is prepared by passing hydrogen sulfide gas through a solution of arsenious oxide, as 2O3 plus 3 hydrogen sulfide, right arrow as 2S3 plus 3 hydrogen oxide. Now, let's discuss an important concept: equilibrium, specifically the Donan membrane equilibrium. This occurs when two electrolyte solutions are separated by a membrane that is impermeable to one type of ion. At equilibrium, the permeable ions are distributed unevenly across the membrane. This results in a difference in osmotic pressure and creates an electrical potential difference between the two solutions. This entire phenomenon is known as the Donan membrane equilibrium. In this context, we define the internal solution. This contains the colloidal non-penetrating ions along with small penetrable ions. The external solution. This contains only penetrable ions. The semi-permeable membrane. This separates the two solutions and allows only the small ions to pass through. How do we purify colloids? The three main methods are dialysis, electrodialysis, and ultrafiltration. First, dialysis. This process separates colloidal particles from smaller ions and molecules, crystalloids, by diffusion through a semi-permeable membrane. The key principle is that colloidal particles cannot pass through membranes like cellophane while ions can. Impurities diffuse out, leaving a purer colloid. The water outside must be changed regularly to prevent the impurities from building up and diffusing back in. Dialysis can be used, for example, to remove HCl from a colloid. Since dialysis can be slow, we use electrodialysis to speed it up. By applying an electric field, we actively pull the charged ions through the membrane, much faster than by diffusion alone. This principle has a critical application. Artificial kidney machines use electrodialysis in a hemodialyzer. Blood flows on one side of a membrane, and waste products are drawn out into a dialysate solution under the influence of an electric field, with the cleansed blood returned to the body. The third method is ultrafiltration. This is a high-pressure filtration process using a semi-permeable membrane. The colloidal particles are retained, while the solvent and small solutes are forced through the membrane by hydrostatic pressure. This too has a vital biological application. Ultrafiltration is a fundamental process in our kidneys. In the glomerulus, blood pressure forces water and small solutes out of the capillaries and into the Bowman's capsule to form the initial urine filtrate, while proteins and blood cells are kept back. Now, let's examine the intriguing properties of colloids. First, the physical properties. Heterogeneity. They always consist of two distinct phases. Visibility of dispersed particles. The particles are invisible to the naked eye, making the mixture appear homogeneous. Filterability. They pass through ordinary filter paper but are retained by finer membranes like cellophane or ultrafilters. Stability. Lyophilic salts are very stable. Lyophobic salts can also be stable if the concentration of electrolytes is low. Color. The color depends on particle size. Larger particles tend to absorb longer wavelengths of light and transmit shorter ones, influencing the color we perceive. Now, the optical properties, and a famous one, the Tyndall effect. When a strong beam of light is shown through a colloidal solution in a darkened room, the path of the beam becomes visible as a bluish cone of light. This is the Tyndall cone. It occurs because colloidal particles are large enough to scatter light. True solutions do not show this effect because their particles are too small. This phenomenon is so useful, it's employed in the ultramicroscope to detect and study colloidal particles. Imagine a light beam becoming visible inside a soap solution with the scattered light visible to the eye. Next, the mechanical properties, specifically Brownian movement. This is the continuous random zigzag motion of colloidal particles within the dispersion medium. It is caused by the uneven bombardment of the particles by the molecules of the medium. This movement is more pronounced for smaller particles, which is why suspensions with their larger, heavier particles do not exhibit significant Brownian motion. Now, the electrical properties. First, electrophoresis. This is the movement of colloidal particles towards an electrode when an electric field is applied. Positively charged particles move towards the cathode, negatively charged ones move towards the anode. Then there's electromossis. This is the complementary phenomenon where the particles are prevented from moving by a membrane, and instead, the dispersion medium moves relative to the stationary particles under the influence of the electric field. You can visualize a YouTube setup where the liquid level changes as the medium moves towards one electrode. A crucial concept is coagulation or flocculation. This is the precipitation or settling of a colloidal solution upon the addition of an electrolyte. The ions from the electrolyte neutralize the charge on the colloidal particles, reducing their mutual repulsion and allowing them to aggregate and fall out of suspension. Visually, adding a coagulant forms a precipitate that traps impurities, and this mass settles to the bottom. We quantify this using flocculation value. It is the minimum concentration of an electrolyte, in millimoles per liter, needed to cause coagulation. An electrolyte with a smaller flocculation value has a greater coagulating power. Therefore, coagulating power is inversely proportional to the flocculation value. Coagulation can also be achieved by other means, through electrophoresis, by mixing two salts with opposite charges, or by persistent dialysis. Let's explore the biological significance of colloidal systems. This is where the topic truly comes to life. Protoplasm is a colloidal system. The very foundation of life, the protoplasm within cells, is a complex colloidal system of cytoplasm, cytosol, nucleoplasm, and organelles. Amoeboid movements. The movement of cells like amoebae relies on the ability of their colloidal cytoplasm to change between fluid sol and more solid gel states, allowing the formation of pseudopodia through processes of endocytosis and exocytosis. Fruits. Many fruits store proteins and starch, which exhibit colloidal properties. Blood. The plasma proteins form a colloidal system that is essential for maintaining the blood's pH and osmotic pressure, which are critical for health. Now, let's appreciate the many advantages of colloids. Colloids allow us to disperse otherwise insoluble materials, making them useful or absorbable. For example, colloidal gold is used in medicine to deliver drugs and antibiotics due to its non-reactive and non-toxic nature. The pharmaceutical industry uses colloids in numerous medicines, such as emulsions of cod liver oil. The paint industry relies on colloids for the preparation of paints. In milk, the colloidal suspension of fats prevents it from being too thick and allows for easy absorption of nutrients. Sewage treatment plants use electrophoresis to remove charged colloidal particles of dirt and mud. The sky appears blue because of the Tyndall effect. Sunlight is scattered by colloidal dust particles in the atmosphere. Asphalt is often emulsified in water for easier application in road construction. When milk sours, fermentation produces lactic acid. The ions from the acid neutralize the charge on milk's colloidal particles, causing them to coagulate and form curd. Soap is a colloid that cleans by adsorbing dirt or emulsifying grease. Countless foods we consume daily are colloids: milk, butter, ice cream, and many more. Finally, we see references to commercial and historical products like colloidal gold and cherry blossom shoe polish, which utilize colloidal systems, along with a mention of colloidal silver. Thank you for joining me on this detailed journey through the world of colloids. I hope you found it as enlightening and engaging as I did. Thank you. See you in the next class.